So we now have an example of this. Consider then a long thin bar of length L with a circular cross section of radius r, and it's held at one support end by a solid support. Here at the other end, a force is applied in the axial direction as shown, but it's applied at the bottom surface of the bar. And we have some material properties. And our question here is, what is the minimum radius of the bar? That is, what r do we need to prevent failure? So our first step is to decompose to find the internal loads. So we learned for an off-center axial force, we can decompose this to an axial load. And then this thing here was a bending moment, RF, and that moment is applied, we say it is applied to a point, and it looks like this. Of course, we could have also drawn that up like this, which is how we're used to drawing it, and we will call that magnitude RF. We then do a cut here, define here n of x. This is very simple. They're pointing the same direction, so n of x equals a negative f. Check, that's what I'm supposed to get. We can do a cut here, make m of x here, pointing upward as we need. And we see there, again, it's in the same direction as RF, and so that gives us m of x is negative Rx, and then we could draw the unknown v of x, but there's no forces here for it to balance, and so v of x equals 0. So that gives us the internal loads in this combined load. We then need to find what the stress is at positions of interest. So we know that for a axial load, the sigma in the axial direction is the force divided by area, and that's everywhere. The cross-sectional area is pi r squared, and so we get this expression here for the force in the axial direction, or for the axial compressive force. Now we also have longitudinal forces in the x direction due to the bending moment, and they're of magnitude negative y times m of x divided by I. We plug in RF for the bending moment, the negatives cancel. For circular cross-sectional area, the I is pi over 4 r to the fourth, so we plug that in and we get this value here for sigma of x. And this is extreme at the top and bottom where y is plus or minus r. So the y cancels out another r. That r that we had here canceled out that first r. And so now we just have that sigma x is plus or minus 4f divided by pi r squared at the top and the bottom of the beam. And we can also see that at the midpoint of the beam, because there is no shear force, v of x is 0, there's also no tau xy in this problem. So we have, with axial load, it's the same everywhere in the bar, and on the bending, we're interested in the top and the bottom of the bar, and so that leaves us interested with the entire top and the bottom, but we'll see that we'll have to add the two together. So we do that to superimpose the stresses at these positions. In this case, they're all in the same direction. So we're just adding these together, and at the top of the bar, the compression due to bending counteracts the compression due to the axial load counteracts the tension due to bending at the top of the bar, and the result is a stress of 3f over pi r squared. Whereas at the bottom of the bar, both bending and axial loads lead to compression, and this gives us negative 5f over pi r squared. So we then do stress analysis at each point. Remember, we had to combine the different types of loads before doing stress analysis, but we've now combined them and we're ready to do stress analysis. So the top of the beam tells us that that we have just sigma x, that's a uniaxial load, and so the sigma 1 and sigma 2 are that load in 0, and tau max is half that value. At the bottom of the beam, it's still uniaxial. This time sigma 1 is 0 because the load is negative, so it gets assigned to sigma 2, and again, tau max is half of that. So we then compare these. We compare the maximum of sigma 1 in the first location and the second location. And of course, the max is that 3f over pi r squared. And to get the maximum of the negative of sigma 2, we compare the 0 to 5f over pi r squared. I say 5 because with not negative 5, because I remembered to take the negative. So that's 5 times that value. And then tau max is the maximum of this and this, which of course is the 5/2. So we have that. And we need all of these to be greater than their respective ultimate stresses. So finally, we were told that material properties had a shear stress of S, whereas both tensile and compressive ultimate stresses were 2S. And our question was, what is the minimum radius? So we're trying to solve for R. So we know it fails when any of these are true, that 3 blah 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 is greater than 2S, 5 blah 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 is greater than 2S, or 5/2 is greater than S. That results in these expressions here for R squared. Once I rearrange to solve for R, we can see that the most constrictive of these is that R squared has to be greater than 5/2 this value, because that's a bigger than 3/2 this value. Therefore, that's a more restrictive because it needs to be greater than both of them. So I then take the square root and turn it around and say R is less than the square root of 5/2 f over pi squared, making that value of R the minimum radius required to support that load. So that's this process in brief for one problem. In general, we won't see that the loads all end up in the same type of stress, in this case where they were all sigma x. So in general, we will probably have different contributions to the Cauchy stress tensor from the different types of loads, and we will see examples of that in the lecture.